Hi, welcome to the 7th lecture on connectedness. This is going to be the almost the third attempt to record this lecture. In the first one I forgot to switch on the recording. In the second one my graphics tablet didn't function properly. Okay, there seems to be some kind of a jinx along with for this lecture. Let us hope I will tide over. Let us go. Today what I am going to do is I am going to prove one of the most basic results about connectedness. If I have two topological spaces x and y, look at the Cartesian product x cross y with the product topology. It's connected if and only if each of the factor spaces, namely x and y, are connected. Okay, this is what we are going to do today. Okay, and we will of course as usual give some applications. Yeah, let's get started. So let quickly do that. X, okay, maybe tau x if you want, but I will not write it later. Tau y, topological spaces, right? And let's look at the Cartesian topology x cross y. Then there is what is called product topology. So the topology tau consists of all open subsets u of x cross y, so that for every element of x, y in u there exists u1 in tau x, u2 in tau y, so that x, y belong to u1 cross u2 that is contained in u. Okay, therefore the basis for the product topology is sets of the form u cross v, where u is in tau x and v is in tau y. Okay, I already changed the notation. U is not a subset of x cross y, u is a subset of x. Okay, this kind of jumping, you will see that. One of the most important properties of the product topology is, let us look at the so-called projection maps. What are they? Pi x from x cross y to x. So pi x working on ordered pair xy is by definition the first coordinate. Similarly pi y. So pi x and pi y. Okay, let us say pi x from x cross y to product topology to x with tau x is continuous. Similarly pi y. Okay, in fact if you are followed by unified view of these topologies, you know the product topology is the smallest topology. On x cross y, making pi x and pi y continuous. Okay, this is an important fact. Okay, we don't need that luckily. Okay, we don't need this, but if you had looked at my unified lectures, you will know we have done all these things there. Right, now let's quickly look at some outcome of these things. The next important result one knows about this is, suppose I have a z tau z is a topological space. Okay, let f be a map from z to x cross y, of course with the product topology. Okay, then any f of z is an ordered pair, therefore I can write it as f1 of z and f2 of z. Therefore f1 is a function from z to x. Similarly f2 will be a function from z to y, right? So this is again a well-known fact about product topology. Okay, f is continuous if and only if f1, f2 are continuous. The component functions are continuous. Okay, these are the facts we will need. If there is anything more I need, I will inform you as we go along. Okay, right. Next thing is how to visualize product thing. Okay, so let us do this. So let us assume this is something like my x and this is something like my y. Okay, maybe I should make it go here. Yeah, right. Now there are two obvious things you can think of, namely let's look at only simplest thing. Let J be the inclusion map of x2 x cross y. Okay, fix yeah, y, let's say y naught in y. So what I give me an x, then J of x must be a point in x cross y. Since y naught is fixed, obvious choice will be x y naught. You follow that? So this J of x therefore is nothing other than x cross singleton y naught. How do I look at this space? This is the space I look at. Suppose this is my y naught, right? Then this will be my, so this will be x cross singleton y naught, right? And similarly, suppose I have an x naught. Okay, so similarly, suppose fix an x naught in x, then I have another inclusion. I will still denote it by j. I do not keep on writing notation to x cross y. What is the map? Y going to, it has to be ordered pair. Since x naught is given, x naught comma y, right? And therefore what is j of y? That will be singleton x naught cross y. This is a subset of, notice that these are all subset of x cross y product space. Okay, so how do I imagine that? I look at it like this. Okay, let us look at an x naught. Okay, and this will be my so this will be my singleton x naught cross y. Therefore what is this point? This point is x naught y naught. Okay, right. Why I want to spend some time, this is just ordinary stuff. Now I want to claim the inclusion maps. Let us say j, let me go back to my earlier color. Let us look at j to, let's say x to x cross y given by x going to x comma y naught. Okay, therefore j of x, I claim j from x tau x to x cross y, the product topology tau is continuous. Yeah, why this is continuous? Because what is the component? J of x is going to be x comma y naught. Therefore what is the first component j1 of x? That is x, that is j. Therefore j1 is a map from x to x, which is identity map of x. And what is j2? j2 of x is y naught. Therefore j2 is a map from x to y, constant map. Right? So both are continuous. j1 and j2 are continuous. Therefore j is continuous. Therefore j is a continuous map from where to where? X to x cross y, so that the image j of x is nothing other than x cross singleton y naught. And similarly the other case, okay, the replace x y naught by x naught and you will get something similar. Do you understand all these things? Okay, so pause, review, proceed. by replacing y0 by x0. Okay, now we are hopefully we are ready for the theorem. What is the theorem? Theorem is the following. Let x tau x, y tau y be topological spaces. Let tau be the product topology on the Cartesian product x cross y. Then x cross y tau is connected if and only if x tau x and y tau y are connected. Is the theorem clear? So how do I loosely speak? Product of space is connected if only if the factor spaces are connected. Okay, this is a loosely way of saying this. Okay, do you understand this? Let us start with the proof. Okay, suppose x cross y is connected. This is my hypothesis. So I want to prove x tau x is connected. Similarly y tau y, right? But this is very easy. Why it's very easy? Remember, I always emphasize the role of continuous maps. They are very important. Functions are very important. Okay, so there is an obvious map, namely pi x from x cross y tau to x cross tau. This is continuous, right? Now what is the image of pi x of x cross y? That is x. And if this is connected, then we have seen the continuous image of a connected space is connected, therefore this is connected. Do you follow that? And similarly y is connected. Okay, pause, review, proceed. Now let's look at the converse. Okay, assume x, I don't write y, tau x etc. x y are connected. I hope this ink works well for you to read. If not, please write it in the comments so that I will resist from using this. Okay, I will not use it later in my lectures, this particular green color. Okay, then I want to prove x cross y is connected. This is a question. I want to prove that. So what is our characterization to prove connectedness? That is, if you give me any continuous function from x cross y tau to r such that f of x cross y is contained in plus or minus 1, then f is a constant. This is what we want to prove. Give me any continuous function f from x cross y to r which takes values only in that two element set plus or minus 1, then f must be constant. Do you understand this? Very good. Now how am I going to prove that? The way I want to prove that is, okay, fix a comma b in x cross y. Okay, so it's enough to show for all xy in x cross y, f of xy equal to f of ab. Then f becomes a constant. Do you understand that? Yeah. Now how am I going to do that? I'll first explain with the proof, because the simplicity of this argument should not be lost by verbose writing. So let me just look at that argument. So this is my x. Oh, sorry, let me just again replace this. So this is my x and this is my y, right? Now let's look at a point. This is my a cross b. Okay, therefore this is okay, this is my b and this is my a. Therefore this object is nothing other than x cross singleton b, right? Okay, and similarly, okay, let's look at this one. Okay, so what is this object? This is a cross y, as we drew earlier, right? Now let's look at a point, any arbitrary point x comma y in x cross y, right? Therefore this, so there it may be like this. Okay, yeah, are you following? Okay, I should have drawn a better picture, but let's not worry about. Okay, so let us look at, now I have not drawn because changing the color etc takes time, so I'm a little impatient. So I have something like a comma b, I have something like x comma y. Therefore what I do is I try to draw this. Okay, this is what, this is b, right? X cross b, right? Now let's draw this. This is going to be singleton x cross y. Do you understand? I'm sorry for the earlier picture. This is the picture I wanted. I was, see, this is why I should think. Okay, right, are you following? Yeah, you could also draw the other way around. So this is my AB, this is my XY, then I could have drawn this, then I could have drawn this also. Okay, this is my AB, this is my XY, right? Therefore this will be what? This will be x cross singleton y, right? And this will be a cross singleton y. Okay, notice that there are dual pictures, but let's not worry about. I just want you to think. Okay, if you are just only after a rigorous, I mean not rigorous, textbook proof so that you can simply memorize, please don't watch my videos. Okay, now I want to prove f of ab. Now remember, since what is my assumption? Yeah, now I already said the map J from x to x cross y, okay, for any fixed thing, this is connected. Therefore the set, this set is connected. Why this is connected? Because that is the image of the map x going to x comma b. So J of this capital X is x comma singleton b. You follow that? I am just looking at this map is connected. Similarly this set is also connected. Okay, the other one is y going to x cross y, the map is y going to a comma y. Okay, that is this map, that is x comma b. This is a comma x comma y, sorry, I am looking at this map. Okay, this one x comma y. X is fixed, I am allowing y to vary. So therefore this map image is singleton x cross y. Okay, and we had already seen these maps are continuous. Okay, these are inclusion maps, either as a vertical line, okay, at a vertical fiber or a horizontal fiber, right? The vertical fiber is x cross, the vertical fiber is singleton x cross y, the horizontal fiber is capital X cross singleton b, that kind of a fiber. Okay, they are all connected. All right, do you follow that? The next thing we know is, let me restrict f to this space singleton x cross b. Oh, I wanted to give understand the picture side. So if I restrict f to this space, then it's a constant, because this is connected, therefore it must be a constant, right? Therefore the value of f at a b, and the value of this, what is this point? This point will have coordinates x comma b. Do you follow that? Yeah, this point is x comma b, and when I restrict to this horizontal fiber, this is a connected set, and f is a function from this connected space to plus or minus 1, the continuous function, therefore it must be a constant. That means f of ab must be f of xb. And similarly restrict f to this, okay, restrict f to this, then what happens? Again, this is singleton x cross y, this is a vertical fiber, okay, therefore it's connected, therefore this function must be a constant, therefore the value of the f at x cross y and x comma b, both points are on the fiber. Do you understand? Therefore f at these 2 points must be the same, but then that follows f of ab must be equal to f of xb, but f of xb must be f of xy, that means f of xy equal to f of ab. The proof is over. Okay, pause, review, proceed. Okay, let me just check whether recording is going on. Yes, okay. Now let's write a proof. Okay, sense. So let me just quickly draw the picture. I may forget this. This is my AB, therefore this is x cross b, and this is singleton x cross y. Yeah, right. Since x cross singleton b is connected, why this is connected? X is connected, that's our assumption. X is connected, and the image of x under the inclusion map, x going to x comma b. So let us say x is connected, the map x to x cross y, namely x going to x comma b, is continuous. Therefore the image under this map, image of x under this map, is x cross singleton b, and it is connected, therefore the restriction of f of f to this space x cross singleton b to x cross singleton b to r, of course it takes values 1. I will simply say again denote it by f itself. This is contained in plus or minus 1, and since f is continuous from x cross y to r, it says restriction to any subset is also continuous with respect to subspace topology. Remember, x cross singleton b has a subspace topology, right? Therefore I know, so this is continuous, therefore f is a constant where on x cross singleton b, right? Now what are the 2 points there? A comma b and x comma b, both are in x singleton b. Since f is a constant, that means f of xb equal to f of ab, or let me write f of ab equal to f of xb. Do you understand? Now argue similarly, f restricted to singleton x cross y, this is the space I am having, so this is x, this one, and this is my x comma b, and this is my x comma y. right? This is continuous and this is connected, therefore f is a constant on where singleton x cross y. Therefore now let's look at the 2 points. X comma y is there, x comma y, and x comma b both are in singleton x cross y. Therefore f of xy must be equal to f of xb. Call this 2. Now let's look at 1 and 2. F of xb equal to f of ab, but f of xb equal to f of xy. Therefore 1 and 2 imply f of xy equal to f of ab. But remember, the ordered pair xy is an arbitrary point of the product space. Therefore I have shown any continuous function from x cross y with product topology to R taking values only in plus or minus 1 is a constant. Therefore x cross y is connected. Converse you had already seen. Therefore it completes the proof. Okay, pause, review, proceed. Okay, now let's look at applications. See, Rn for any greater than or equal to 1 is connected. Why? Because we already know R is connected. Therefore by induction R2 is R cross R is connected. Now remember, there is a subtlety here, you should be aware of that. Okay, the subtlety is when I say R2, this is with respect to the standard topology, that is standard Euclidean topology, which is given by either a D2 metric, but we know the metric is induced by D1, D infinity, they are all the same. Therefore let me say it's a standard topology, right? When I say R cross R is connected according to the theorem, this is a product topology. So you have to know the standard topology in R2, which is given by either D1, D2, D infinity metric, they all give the same topology, as we know, is same as the product topology. If okay, in my that, do you follow that? Why that is true? Because remember, D infinity, okay, metric, what it induces is actually product topology. Because the bases, the open balls in R2 with the D infinity metric are rect, okay, are squares, right? You have a point x a comma b, then this will be a minus r to a plus r. This is a minus r, a plus r, okay, this will be b minus r to b plus r. Okay, so I have a minus r to a plus r, and here I have b minus r to b plus r. Therefore that product is going to be this one. So this is a minus r to a plus r cross b minus r to b plus r. You see that how many subtle things, okay, are never explained. Okay, you just assume the moment you say that R2 the topology, etc., you assume. Okay, so now this is a, but this is okay, this is a basis for a product topology also, this class. So this is D infinity metric, okay, open balls at a comma b comma r, okay, this collection a b in R2 and R positive, this is a basis for R2 with the D infinity topology, as well as R cross R with the product topology. Okay, so in the product topology I would explain this, okay, but remember this, okay, otherwise take it as an exercise to prove this. But those of you who are little less confident about these things, just understand there is a subtlety. Okay, I want to prove R2 with the standard topology is connected. What I know is R cross R with the product topology is connected. R cross R, as I said, I denote by R2, no problem. But the topologies may be different. This is a standard topology on R2, here it's a product topology on R cross R. But luckily, these two topologies are the same. Okay, that's a subtle point you should be aware of. Yeah. So using this and induction, similarly, see the same thing with Rn, write it as R cross R cross R. Okay, this Rn n times. Again, similar proof shows the standard topology on Rn is same as product topology. Okay, right? And this is the therefore this is a product of connected spaces. By induction you can see if x1 x2 xn are connected, then x1 times x2 times xn, okay, the Cartesian product with the product topology will also be connected, so it will follow. So the only subtlety is this. Okay, you would see in my video on product topology I would have proved it. The proof is actually easy. Using the definition of product topology you can actually prove it, okay, without even looking into basis, etc. There are much easier proof, but let me not get into that now. I want to concentrate on connectedness now. Okay, the second example I want to talk about is I want to prove, this is the second application, a punctured plane, or more generally, all of you must have okay, so all of you must have been learning complex analysis simultaneously, or you must already learn, you know what is meant by punctured plane. Take R2 and remove the origin. This is the origin, okay, it's not 0 0, it's 0 0. Okay, remove the origin. More generally, okay, let's look at Rn and remove the origin. Okay, so we want to say this is connected. If n is greater than or equal to 2, this is connected. Remember, when n equal to 1, r minus 0 consists of two things. This we already know, this is not connected. So the important thing is n greater than or equal to 2. Alright, okay, how do I prove this is connected? Okay, the trick is the same. Remember, in the case of R2, I want to go slow, please follow me. So in the case of R2, let us look at this point is removed. This is removed, right? Now intuitively you can see that if I have 2 points, okay, any 2 points, I can put the line, or it is here, I can put this line, or it is here, I can put this. Alright, do you see that? Okay, now suppose it's exactly like this here. What will I do? In that case, I will go here and come here. And similar thing, if it is here, I'll go here. Let us say it's here, I'll join this. So in R2, what I'm saying is I'm giving an elementary geometrical way of looking at. One can prove this rigorously. Okay, R2 minus Singleton. This is connected because any 2 points. Let me write it as P comma Q, where P is an ordered pair in R2, Q is also an ordered pair. In 2 points P and Q can be, okay, or are elements of a connected subset. What does it mean? Let us look at this. This to this is a connected set, this to this is a connected set, because we have already seen line segments are connected, and these two connected sets have a point in common. That means their union is connected. Therefore this point P this point Q, they lie in a connected subset of R2, right? And we had already seen that was first application after characterization of connectedness in terms of continuous functions, that if X is a space so that every 2 points P and Q lie in a connected set, then X is connected. This is a fact we had already seen. This is the first application. Therefore R2 will be connected. Do you follow that? Okay. Because this has a this kind of logic has a very important reason why I did that, but let's not worry about. So I leave it as an exercise to prove this rigorously. Okay. Okay, one should also have the geometrical thinking. Okay, but I'm going to take an easy way out. The easy way out is, remember, if this is the punctured plane, if you give me any point x comma y, I can write as r cos theta and r sin theta, where r is positive and theta lies in 0 to 2 pi or in r, it doesn't matter. You understand? Therefore it already tells me any point is going to be, okay, I want to write r2 minus 0 as the continuous image of a connected set. The connected set is going to be product of connected spaces. Okay, so this means what I have, can you think of this? What? So I want to say my r2 minus 0 is a continuous image of a product of two connected sets, spaces. Can you think of? Where does r vary from 0 to infinity? Where does, as theta varies over r, cos theta, sin theta, what do they form? They form a circle. So I know this is connected, this is an interval. We had already seen S1 is connected, right? Therefore this is connected. And from here to R2 minus 0, I have obvious map, r theta going to r cos theta, r sin theta. Okay, and this is a continuous map. Okay, it requires a bit of analysis, but let me just be a little sloppy over that. Okay, I will show you a way without being sloppy, even in Rn case, n greater than or equal to 2. Okay, but for the time being I'm just trying to motivate the generalization for Rn minus 0. Okay, so that this is continuous, you have to see that is r theta going to r cos theta is continuous, r theta going to r sin theta is continuous. That's very clear. R going to r is continuous, theta going to cos theta is continuous, therefore product of continuous function is continuous, etc, etc. And this is a product space, you understand? Therefore this is continuous, right? So the image of this, so the images of this map is r2 minus 0, therefore this is connected. Okay, that's a proof. Now I want to generalize this argument to Rn minus 0, where n is greater than or equal to 2. So how do I do that? So let's start with any vector x in Rn minus 0, right? What do I want? I want to know about r. Here r is nothing other than the length of the vector, or the distance between the vector xy and the origin, or the norm of the vector, if you think of this, because all of your MSc students, so you should know the norm. Okay, therefore one way to do that will be, I can think of norm x. Then let us look at cos theta sin theta, that lies on the unit circle. So how does it picture is like this. So I have this is my circle, unit circle, x squared plus y squared equal to 1. Now start with any vector. Okay, this distance is r, and this is my cos theta sin theta, and similarly take any vector here. Okay, then this is your r, this is your cos theta sin theta. Do you understand that? So what all you have to do is, in the same direction, let that vector, the line joining 0 and the vector, look at where it cuts the unit circle or the unit sphere. You understand? So that trick is what I am going to do. Therefore, given any x non-zero, okay, let me look at x by norm x. Then this is a vector in Sn minus 1. And remember, now n is greater than or equal to 2. Therefore, yes, when n equal to 2, it is a circle S1. And in general, it's a sphere. We have shown these are all connected. Okay, already seen. Right? Therefore, do you see a map now? What is the map now? So 0 infinity Sn minus 1. Remember, again n is greater than or equal to Rn minus singleton 0. The map is R, the unit vector goes to R times U. This is a unit vector here, right? Yeah, and this map is continuous. Why this map is continuous? See, R going to R times U. This is, we want to say this is continuous. Yeah, do you follow that? Yeah. Why this map is continuous? This is again a very subtle argument. Say, remember the scalar multiplication R to Rn to R, then the scalar multiplication namely, let me write it as R and x going to R times x is continuous. Okay, notice that how many subtle things are never explained. You simply tend to assume. We are using all those things. That proof is easy. Okay, so this scalar multiplication is continuous. Okay, take it as an exercise. Okay, use epsilon delta definition or sequential definition. Okay, all right, are you following? Yeah, this is going to be R x1 xn going to R x1 R xn. Okay, this is continuous. This is therefore Rx minus Sy. Okay, if they are close is what I want to know. Okay, this is Rx. This is exactly the what is it? Convergence of product sequences. Same argument. Rx minus Ry minus Ry minus Sy. That's less than or equal to R times mod x minus y. If you want to put a modulus plus modulus. Okay, norm of y times modulus r minus s. Right? So if Rx is near to Sy, okay, then you can make this continuous. Okay, just this is just idea. With this you should be able to work out. Okay, this is an exercise. Okay, come back. So the scalar multiplication from R to Rn to Rn is continuous. Therefore its restriction to 0 infinity cross Sn minus 1, these are all subset to Rn is continuous. Right? You follow that? And call this restriction as f. And what is the image of f of 0 infinity cross Sn minus 1? I claim it is Rn minus origin. That is very clear, because if you give me R and U, then R times U, okay, is the norm of R times U will be R times norm of U, which will be R, which is positive. Therefore this lies in Rn minus 0. Okay, now give me any vector x in Rn minus 0. All of you already know, take U to be x by norm x. Therefore R to be norm x. Therefore norm x, x by norm x, this belong to 0 infinity cross Sn minus 1. Okay, where does it go to? It goes to x. Therefore it's onto, right? Therefore I have proved Rn minus singleton 0 is connected. So pause, review, proceed. So third application is any annular region See, this will all be, you see that if you are doing complex analysis or you are done, you will see all these things you would be using. Okay, punctured plane is connected, annular region is connected. Okay, you may or may not have seen a very rigorous proof. Now you are seeing all these proofs here. That is very clear, because what is annular region? It is set of all points x in Rn. So that fix an r less than r 0. This will be little r less than norm of x, or maybe less than or equal to also. Maybe less than or equal to. Okay, this is a closed annular if equal to is allowed, otherwise it's a annular. Okay, the picture will be like this. So this is R, this is capital R, the region is this. This is the region, shaded region. Okay, this is connected. Why? That is the image of the interval R cross R to Sn minus 1 to Rn. Right? So any row and a vector u going to row u. And what is norm of row u? Row times norm of u, which is rho. But rho lies between R and R. That's it. Okay. There are few others, but I think this is enough. There is quite a bit of things. As you can see, just a learning theorem. Okay, let me just stop it and come. So today's important lesson you can see is there are a lot of subtleties which are never explained. You take it for granted. Okay, and since I explained, you may be a little overwhelmed. You may think it's difficult. No, you learn these things well. You don't even have to remember. Okay, it becomes part of you. Like, okay, when you are in second standard, you learned multiplication table. So you have to memorize, you have to keep on working a lot of problems. Now you don't have to remember the table. The moment I ask you what is something like A cross B, you know the answer. If A and B are one day, single digit. Okay, so that becomes automatic. So similarly, if you go through this kind of arguments very carefully without worrying about I will remember, you should not worry about that. Okay, don't. Without worrying about it, you just go through the argument. Okay, that will become part of you. Your subconscious mind will understand such things and it immediately goes through the argument on its own. Okay, I hope you all enjoyed the lecture. Stay tuned. We will come back with another important fact.